Hello class, I'm working out of your Algebra 2 book 3.5. We're working number 32. Look in your book at the problem with me. A sporting goods company wants to make the maximum profit on its top-of-the-line softball and baseball gloves. They make $50 per softball glove and $30 per baseball glove. They have a total of 1,200 foot squared of leather and 800 work hours available. Each softball glove requires 5 foot squared of leather and 3 hours of work time, while each baseball glove requires 2 foot squared of leather and 2 hours of work time. What is the maximum profit, and how many softball and baseball gloves should be made to generate this profit? Alright, so we need to assign a variable for both softball and baseball gloves. So we could assign X for softball and Y for baseball. And every time they make a softball glove, they make $50. And every time they make a baseball glove, they make $30. And this is the profit margin expression. So we need to decide what the profit margin expression is. We're going to come back to this and use this at the end of our problem. But we have some constraints. They don't have an infinite amount of work time or man hours to use, and they don't have an infinite amount of leather to use. And each time they make a softball glove, it uses some of their leather. And each time they make a baseball glove, it uses some of their leather. So let's look from the problem for softball. I'm going to build some kind of chart and think that through. Softball is X, and then baseball is Y from our assigned variables. And every time they make a softball glove, it's 5 foot squared of leather. Every time they make a baseball glove, it's 2 foot squared of leather. So those units match. We're going to build an equation with those two units. And to build that equation, we're going to say, okay, they're going to make some amount of baseball gloves, and every time they make one, it's going to use up 5 foot for the softball glove, and every time they use leather to make a baseball glove, it's going to use up some amount of their leather for that. And from the problem, the total amount of leather they have to use to make these is up to or equal to 1,200 foot squared of leather. So that's how we build that inequality constraint. Now for hours, it is 3 hours of work time to make a softball glove. And it's 2 hours of work time to make a baseball glove. And so for that constraint, we're going to say, okay, for every time they make a softball glove, it's going to cost them 3 hours. And they're making baseball gloves at the same time, and every time one of those get made, it costs them 2 hours. And they only have 800 hours in the constraint for a total amount of man hours. They want to make a profit, so 2 more constraints are, hey, for the softball gloves, we want it greater than or equal to 0. And for the baseball gloves, we also want it greater than or equal to 0 to break even or make profit. So we just built 4 inequality constraints. And to start solving for those, we're going to find points on the graph. So we're going to just take 5x plus 2y less than or equal to 1200. We'll start plugging in 0 for x. And this goes away. We divide by 2, so y is less than or equal to 600. So we have a plotted point here, 0, 600. And then plug in 0 for y. And this goes away, and we have x is less than or equal to something like 240. We're going to go to our graph and graph that. My graph says 1, 2, 3, but we'll make it 100, 200, 300, and we can do that. So it's 0, 600, and 240, 0. Graph is going to kind of run right here. Remember, because we want a profit, we're working in the positive region, quadrant 1. So that's a given. And our inequality constraint right now is going to shade under because it's less than or equal to 1200 for the total amount of leather they have. So this is the leather graph. Okay. Now if we go back and look, we did the leather plotted points. And we're going to now think about the work hour plotted points. I'm going to plug in 0 for x. Okay, so that goes away. We have divide by 2, and y is less than or equal to 400. So we have a plotted point, 0, 400. We're going to plug in 0 for y. And this goes away, and we have something like x is less than or equal to 266. We're going to round off on that one. It's not a perfect whole number, but for our graphing purposes, it'll be fine. Okay, so if we graph these, it will fall at 0, 400 and somewhere around 266, 0. So somewhere in here, and we're going to have an intersection happen on our two lines at some point. Can't quite see it very well. Okay, so our intersection point is interesting right there. We're going to see algebraically and mathematically where these fall. So how do we do that? We take our two constraints and set them together and use elimination. We've done this. To find our intersecting points. And it works out very nicely to multiply this by a -1 all the way across. And we'll get, it goes to 5x plus 2y is less than or equal to 1200. And then we'll have a -3x minus 2y is less than or equal to -800. Okay, these go away. we have 2x is less than or equal to 400, and then we will get x is less than or equal to 200. Okay, we have an s. Plug our x in for the first equation, x at 200. We'll solve for y. Okay, so that's 1,000 plus 2y less than or equal to 1,200. Subtract 1,000 from both sides. And we're going to have 2y is less than or equal to 200. And the y here is going to be less than or equal to 100 when we divide by 2. If I hit my smart keys, it'll throw out my recording, so I'm going to have to work where I have room. So mental math that. Okay, so our intersection is at 200, 100. It's about there on the graph. If we look. And what happens is our first shaded region has to go away because it's no longer viable based on our graphing. Our new shaded region is now this for profit margin. And to find that profit margin, we're going to take these plotted points for our graph that we found, and we're going to test them in the original profit margin expression that we built for x and y. So we're going to see where the maximum profit will land with 50x plus 3y. How do we do that? We have 50x plus 3y plus 30y. Excuse me. Okay, 30y equals the profit of xy. If we plug in $50 times 240 plus 30 times 0 from here, let's test that for x and y. That spits out about a 12,000. If we plug in 50 times 200 plus 30 times 100 from our intersection point that we found through elimination, that spits out a 13,000. If we plug in 50 times 0 plus 30 times 400 from here, from our other expression, we've tackled a plotted point from each expression. That is also 12,000. And we find from our intersection point, making 200 softball gloves and 100 baseball gloves with the materials and man-hour available, we have $13,000 profit. So this is the maximum profit, and we would say that maximum profit at 200, 100 of $13,000. So build your constraints, find your profit expression, solve for X and Y, graph, test your points. All of those steps are included in finding maximum profit problems. I hope this helps, and I will see you soon.